Good afternoon, everyone. My name is Shaza Zeitouni from the Technische Universität of Darmstadt, presenting today our SoK paper on the challenges and opportunities of secure multi-tenant FPGAs in the cloud. I'll try to summarize our work into the following points, starting with an overview of FPGA deployment models in the cloud. Then we discuss the adversary model and challenges of FPGA trusted computing, and conclude with future research directions. FPGAs are integrated circuits that can be configured by end users to implement different digital designs. Recently, they have been adopted or deployed in the cloud as hardware accelerators. We focus in this SoK on the security aspects of FPGA as a service deployment model, in which the clients have the freedom to configure the FPGAs to accelerate their own applications. In this model, the clients upload the FPGA configuration file, which is used to configure the allocated FPGA by the cloud operator. In this scenario, we have two major security concerns. First, the clients are forced to reveal their hardware designs, which might be intellectual proprietary designs, to the cloud operator or cloud service provider. On the other hand, FPGA designs may contain harmful logic that may pose serious threats on the availability of cloud services or the security of co-clients. To boost the FPGA utilization in the cloud, researchers have proposed to split the FPGA fabric among different clients. This is feasible due to the partial reconfiguration property of FPGAs. So the FPGA is split into one static region for the shell and several reconfigurable regions assigned for different clients. The shell, or called the FPGA hypervisor, provides the required physical infrastructure like clock signals, interfaces to the host, and other management resources. So the shell is usually provided by the cloud service provider. This model, the Spatial multi-tenancy, is not adopted currently by cloud service providers. In the other model, acknowledged as Temporal multi-tenancy, the entire fabric, except for the shell, is dedicated for one client at a given time. Note that this temporal multi-tenant deployment model is currently the one adopted by commercial cloud service providers. Next, we briefly discuss the part of the adversary model related to the FPGA securities. In the cloud environment, co-clients are distrusting. Further, the cloud service provider does not trust the clients, as they may launch different attacks, including non-FPGA specific attacks like, for example, cache, side channel attacks, or Rowhammer attacks, or other sort of attack that are FPGA specific, in which the clients can freely configure the FPGA fabric with malicious circuits. On the other hand, the client is enforced to reveal their IP design that will be configured on the FPGA, and consequently the data that will be processed on the FPGA is also revealed. Next, I will briefly present an overview of the different attacks, starting with the attacks that are also applicable in the general purpose computing platforms. So these attacks are demonstrated on experimental Intel platforms. In the setup, the FPGA accelerator has a local cache that is coherent with the CPU last level cache. The FPGA also shares the main memory with the CPU. Nevertheless, FPGA reading from the main memory does not affect the last level cache, nor the FPGA can perform cache line flush instruction. So this makes the Rowhammer attack conducted by the FPGA more efficient compared to the CPU version. As for cache side channel attacks, the attacks are possible in both directions. from CPU to FPGA, and from FPGA to CPU. For these attacks, typical defenses adopted in the general-purpose computing paradigm can be also deployed. Now coming to the FPGA-specific attacks. Denial of service, side and cover channel attacks based on changes in the operating conditions like power and temperature have been demonstrated in the spatial as well as the temporal deployment models. These attacks are conducted by unprivileged malicious clients using configurable sensors and power virus circuits. However, they can be also launched by a privileged FPGA shell. These attacks are comparable to power drop and power leakage attacks on the CPU that exploit the access to the dynamic voltage and frequency scaling interface. However, the defenses are different. These defenses can be categorized into runtime defenses and preventive or static defenses. Runtime defenses may use configurable sensors to detect power or temperature changes, or use configurable power viruses to hide power consumption patterns of the protected designs. These solutions should be tuned based on the protected hardware design and the targeted FPGA. On the other hand, virus scanners as a preventive solution aim at preventing the configuration of malicious logic circuits on the FPGA. These virus scanners should be kept up to date in order to detect new ROG primitives, and note that not to mention that they need access to plain text configuration file. Coming to solutions against IP piracy on cloud FPGAs, researchers propose to extend the shell to perform the following tasks. These solutions, these tasks are exchanging secret key with the client, decrypting client bitstream, and partial configuration of the client application on the FPGA. These solutions require the FPGA vendor support and work for temporal multi-tenancy model. Nevertheless, these hardware designs with malicious primitives will go undetected since client configuration files are encrypted. This also required that the shell, the FPGA shell or hypervisor, to be trusted. So to summarize the main challenges of trusted FPGA cloud computing, first, enabling trusted configuration and execution on cloud FPGA. This should be done with minimal changes to the FPGA architectures under the assumption of untrusted FPGA shell. On the other hand, malicious hardware designs should be prevented from configuration on the FPGA. The most promising general solution, as we saw earlier, are the virus scanners, which require access to plain text configuration files. One alternative would be to integrate virus scanner capabilities into the FPGA toolchains. This, however, comes at the cost of reducing their flexibility. We summarize the future research directions into the following. First, investigating the trusted computing based on FPGAs that is required to establish trusted configuration and execution on cloud FPGAs. The second direction would be hardening cloud FPGAs against remote physical attacks with minimal changes to their architectures, having into consideration untrusted FPGA shell and untrusted clients. With this, I conclude my talk. Thanks for your attention and ready to take your questions.